In the last couple of videos we looked at using a zener diode to set a voltage at part of a circuit. So in this case it is where the zener diode meets this resistor. This is a really high value resistor. It's a 22,000 ohm resistor, so of course there's a lot higher value out there, but for simple circuits like this it's a pretty high value. So in any case, we have 18 volts at the rail there. That's what I have set at my power supply, is 18 volts. It's a tiny bit off. And so this is a 9.1 zener diode. Even with this high value resistor, we have about 9.19, so 9.2 volts at this point. So in any case, we have the voltage basically that it is rated for. And so 9 volts should light an LED pretty nicely. So we'll put the anode, the long lead, to where the resistor there and the zener diode meet, and then we will take a 470 ohm resistor, because that is a resistor you can put directly across the power supply of 9 volts, and it will limit current enough to keep an LED from burning out. But there you can see the LED really is not very bright at all. It's extremely dim, and that's because to set the zener diode I'm using a higher value resistor than I need to, but this is to prove a point that we need a certain amount of current through the zener diode to hold a voltage, and having a load will suck that voltage down. So we will measure that. I'm going to slip under here. Actually, I could go to the resistor, but I'll slip under there, go right to the zener, and we'll see the voltage across the zener is now only 2 volts. So we lost a lot of voltage because not enough current is going through the zener. So we're going to add an NPN bipolar junction transistor to take that voltage and amplify the current that that voltage can provide. So now, the transistor circuit we're going to wire is called an emitter follower. And we will begin by taking a gray jumper. Color doesn't matter. Jumpers, they conduct the same no matter what color they are, but it's good to color code them so you know where they're coming from, to use different colors that come from different sides of the power supply and whatnot. So in any case, we got the jumper there. This is a 2N2222, an NPN transistor that is pretty commonly known. I use it in a lot of my videos, mostly because it's commonly known and commonly available. But so let's do the pin layout first. The left pin here is the emitter. There's the flat side. Left pin emitter, middle pin base, right pin collector. So I want the emitter down one spot and the collector up one spot. So I'm just going to turn it this way and plug it in. So now the collector of an emitter follower goes directly to the positive rail. So a lot of other circuits, there's resistance, maybe even the load between the collector and the positive rail. For the emitter follower, the collector goes directly to the positive rail. So now what will limit the current is the resistance that we have over here. And so to begin with, we're going to take a 2,200 ohm resistor. Exact value does not matter too much, but since we're dealing with 18 volts at the power supply, even though we're going to drop the voltage here, I think this will be a good value resistor because we can put this directly across 18 volts. So in any case, that's a 2,200 ohm resistor. The colors don't look very good, so these are cheap resistors, so don't really try to read the color code. That second one is red, but it's some weird color on here. So in any case, right now we can take our voltage readings. We're done. The resistor will set a voltage at the emitter there, so we're back far enough, and the power supply is off. I'll have to turn that on. So it's on now, and again we'll have 18 volts at the rail, and then probably 9.2 volts right there. That goes to the emitter of the transistor. So the base of the transistor, from base to emitter, we lose about 0.7 volts. That's just the way it is. And there you can see we're about 0.7 volts lower. So now we want to improve this. We want that same voltage that we had there. And what we can do, I talked about this in the last video, so if I yank this, we'll cut the voltage to the base of the transistor. So now it's not going to conduct. There'll be no voltage, which we can measure right there. And there's 0 volts there. Now the transistor is off because it's not getting a signal. So we're going to take a rectifier diode, and actually we didn't have to remove that jumper, but it's a good idea, especially if the power's still on. We definitely need it off if the power is still on. So we will move this over there, and we are going to add a rectifier diode. So now the rectifier diode, it's forward bias, so the black stripe is towards the negative side of the circuit, the side without the stripe, the anode, towards the positive side, and the black stripe is the cathode. So zener diode works reverse bias, and rectifier diode works forward bias. Their voltages are going to add up, and we'll look at that after we replace the jumper to the base of the transistor. And it's kind of a tight fit right there. There we go. That went in actually not too bad. So now we will back up. So just like we have the 0.7 volt loss of the transistor from base to emitter, now we have another 0.7 volts that the voltage has to go through to get to the zener diode, where it raises it to about 9.1. So actually it's been 9.2 lately. So we'll look at that. It's still 9.2 across the zener diode, but now we have another diode adding to the voltage, and now you can see it's looks like it's about 0.5, probably because of low current that it is blocking in addition. So now we actually have 9.7 volts, which works pretty nice actually, because we're losing about 0.7 volts here. So we will look at this spot here. Actually, I gotta go to the negative rail, and there we have spot on 9 volts. So this actually worked really well if you want exactly 9 volts. So now let's add the LED. As we saw before, it was really dim before, so we're going to put the long lead, the anode, to the emitter of the transistor. I'll try not to block your view. There we go. And short lead, the cathode, we're going to go down 1 row. And now we are dealing with an actual 9 volts. So it's going to be a solid 9 volts. So 470 ohms is going to be good enough to keep the resistor from getting too hot, and it will limit current for the LED. And there you can see it's a lot brighter. Before, when we just connected it directly to the zener diode and this high value resistor, there was too much current that was cut down from the resistor. Not enough current to light up the LED brightly and to keep 9.2 volts in this case with the zener diode. So now we don't have that problem. Now the emitter, see if I can get in there. So I'm going to the emitter of the transistor, connects to the long lead of the LED. You can see it's holding, oops, I thought you could see the meter. So anyways, that made it easier for you to see where I'm sticking the probes. But there we go. It is holding that 9 volts really well. And so that's why we're using this. The signal is weak, but we give that signal to the transistor of the voltage. We do need this other resistor, at least it helps. Some loads I think you'll do just fine just with the load, but it's good to have this resistor here to help set the voltage at the emitter. But the current can go through this resistor and through this load independently. The transistor lets through whatever current it needs to, as long as it can, to keep the voltage at the emitter the same as the base voltage minus 0.7 volts. So we used a rectifier diode to add about 0.7 volts. Looks like it's about 0.5 volts actually, and we can measure that directly too, the voltage across it. So yeah, 0.546. This is low current. If we use the lower value resistor here, it will go up. We can go down, as I said before, to 2.2 kilo ohms, 2,200 ohms, because it will get a little too hot, just a tiny bit too hot, but you can put it directly across the rails. It won't get to the maximum wattage of a 1/4 watt, but it'll be a little more than 1/8 of a watt. It's recommended you keep resistors at about 1/8 of a watt or less, but you can go up, especially for short periods of time, to a 1/4 watt and be okay. the life of the component may go down. So, but in any case, hopefully the circuit made sense. I've been leading up to this circuit in my previous videos. So if this circuit was just completely confusing, go through the videos I've been posting the last, I think, 4 days, and I've been building much similar circuits, but more simpler circuits in those videos. But ultimately, these are just small circuit fragments, each one of these parts of the circuit that are just put together, you know. And so if you understand the fragments, then understanding the complete circuit will be really easy. So thanks for watching, and I will see you in the next video.